All right, this is an example demonstrating for the first time the non-commutativity as a physical result and not just mathematics. So this physicist, the lady Valentina Parigi, she's fluent in French because there's an interview with her, which she started out in Italy, I think, at the Italy lab. Maybe she's from Belgium or something. Anyway, so the researchers, so basically it's in this math magazine. When you subtract, you get more than you started with. And so quantum weirdness, so what they do is they start out with the laser, and then they have this rotating I don't know if it's a crystal or something in it that causes the light to be scattered like sunlight. And then when they subtract, they use a quantum half silver mirror to split the photon, split one photon. And then here they're measuring the energy, the amplitude, intensity, and then they get the average number of photons. So when they subtract the photon, they actually get more. They have an increase in the average number of photons. And so then they prove that then they add the photon and you get 2 photons. And then when they add and then subtract, they get more than they should. They should just get 1 photon. So the 0, it's over 0 would be 1. And then they subtract and then they add, they get a different amount. Okay, so this shows how they do it. So in order to subtract a photon, they use a low reflectivity beam splitter. And then to add a photon, they use a nonlinear crystal for a down conversion. So you get 2 photons that they have half of the energy and twice the wavelength. Now, so they're talking about how this is they've proven the non-commutativity. Oh, Parigi, her name's actually, Valentina Parigi. That's what I said, right? Yeah, Valentina Parigi. And so the final state depends on the order in which the operations are performed. The result is a striking confirmation of the lack of commutativity in quantum mechanical operators. The authors present the strongly counterintuitive result that under certain conditions, the removal of a photon can lead to an increase in the mean number of photons. So by mean number, they're squaring the amplitude to get the number of photons and also the probability distribution. So that's the number of photons. Okay, so then they say, oh, this can be used for quantum engineering and cryptography and computing and stuff like that. All right, and she's doing quantum information, Dr. Valentina Parigi, and she's using complex network theory. So, so when they used a coherent state of just the laser light, then nothing changed. So that's why they have to use this spinning diffraction to, supposedly create a random state of just thermal heat light. And so here they're showing the distribution, the density matrices. And when they subtract one photon, you get a broader photon number distribution. So it's more closer to 2 photons than to 1. So the 1 photon is the average, the distribution between 1 and -1. So that's the squaring. That's why it's squared. Oh, that's kind of cool. You can see that. Okay. So then they show with the laser, it doesn't change. If you change the subtracting or adding, if you subtract it, it doesn't modify the distribution of the mean number of photons. Now, I have a very strange interpretation of this. So when they use so now we go to the transactional interpretation, which is the retrocausal model from Olivier Cosa de Beauregard, and John G. Cramer then picked that up. And today I was corresponding with Ph.D. researcher Ruth E. Kastner, who has added on to John G. Cramer's model here. So he explains, if you use a half-silvered mirror, like they used in this experiment, to subtract the photon, it's a probability that it'll pass through or be reflected. But because it's a probability, it will also do both at the same time, which means that it's entangled. When that photon is being subtracted, it's actually causing it to be entangled. Now he says that when the photon comes back to the same path that it was reflected as an entangled self-interference, then they can subtract or they can add together. But and so when they're superimposed as self-interference, then what happens is that you have to include the imaginary part, that is the reverse time, as the square root of 1. And so this is the non-commutative phase. And it's because of that entanglement of the square root of 1 from the imaginary part of the three-dimensional vector then in the complex state function, that's why you get an increase of the photon. The mean number of photon increases to over 1. It's more than you started out with when you subtract, because the entanglement is a self-amplification. This is the consequence that the average states are complex with the complex weighting factors. So this is before you square it. So when they're squaring it, see the probability, the density, it includes the it broadens it out because it's including the negative number of the -1 as the imaginary part of the complex variable. See, this is what this is, at -1 right here. And then that's why you get a lower amplitude, but it broadens it out for the number of photons. And so the virtual, what Dr. Ruth E. Kastner was explaining to me is that the virtual photon has a spin of 1, and so it's not, it would have an equal probability as with the photon. And so the entanglement is a reverse time as a virtual photon because it has an equal probability. This is my interpretation based on this retrocausal. And so the superposition can result in a net time displacement that's quite different from the elapsed time experienced by the external observer. So the system has been translated forwards or backwards in time. This is the relativistic effect. So the observer is the amplitude as the energy of the photons, but the actual photons to themselves have increased because they don't depend on any external observer as the amplitude squared for the probability. And that's why you have the difference between the number of photons with the probability. So you can see this. So They don't show the math, but actually, yeah, okay, this is the whole article. So this is essentially what we do in meditation, is we are, by turning the light around, we're essentially creating a space-time mirror within, we're subtracting the light that would normally go out of our eyes, and we're causing it to self-interfere with itself by reversing the direction, because that's what the entanglement is. So you're reflecting light back onto itself, but when you're doing that, you're also causing a complex entanglement. So if you think of space-time is itself the mirror. And that's what this last part is right here. That there's a translation forward or backward in time with respect to the observer. So the net time displacement is quite different from the elapsed time experienced by the external observer. So you can go forward in time with respect to your external observer, while you're going backwards in time internally through the subtraction of the light, because you're reversing your thoughts, which is essentially a space-time mirror that's like a splitting of the photon, and then it causes it to entangle with itself. So this is my take on that experiment, and maybe no one agrees with me, who knows, I don't know, but this is my take on it, by reading John G. Cramer and corresponding with Ruth E. Kastner today, and in the past I've of course I've uploaded videos that go into that complex. I'll link to that video I posted before, that it goes into the complex math a bit more. So so the quantum weirdness is that, okay, so if we click on this link right here, so it says right here, in mathematics, the commutative law states that, in essence, changing the order doesn't change the result. In ordinary arithmetic, addition is commutative. 3 plus 2 gives the same result as 2 plus 3. So it's very, it's like the simplest thing you can think of. But they're saying no. They've just proven that it's the most direct demonstration of lack of commutativity that I am aware of, said Robert Boyd of the Institute of Optics, University of Rochester. Subtracting a photon changed the beam's quantum state, increasing the mean number of photons. Yeah, they put a spinning glass plate, making the laser beam behave more chaotically like ordinary sunlight. Even though they didn't know the number of photons in the beam, they could determine the mean number of photons using the photo detector, photomultiplier detector, or quantum state detector. I think that's a photomultiplier detector. So there you go. That's my take on it, that there's a secret to this quantum weirdness, that they're not going into that secret. But John G. Cramer, he does go into it, and he gets that's originally from you have to include the relativity, and that's pretty wild. This is what I'm talking about, is the relativity is right in the light. In each photon, there's already relativity. So the photon has that non-commutativity, even though it's a one spin. It's different based on whether it's internal or external. And that's where it's really fascinating. A net time displacement. And so that time displacement is what's creating the interference that causes the increase in the photon. So it's like a really simple experiment, but at the same time it really demonstrates like the mystery of quantum physics through the non-commutativity. So this quantum weirdness, non-commutative quantum mathematics, non-commutative quantum math. When subtraction gets you more than you started with. Okay, thank you very much.